Okay, Professor, I'm gonna start the intro of you, and we're gonna collect all the questions in YouTube Live, and at the end of the talk, I'm gonna pass the questions to you after you finish. Uh, okay. Hello,
Thank you.
everyone. Hello, everyone. Welcome back to our DDLC seminar. Today, we have Professor Francisco Bullo as our invited speaker. Francisco Bullo is a distinguished professor of mechanical engineering at UC Santa Barbara with affiliations in electrical and computer engineering, computer science, and the Center for Control Dynamic Systems and Computation, and also dynamic neuroscience program. His research focuses on modeling, dynamics, and control of multi-agent network systems, with applications spanning robotic coordination, power systems, distributed computing, and social networks. He has authored 4 books, including Distributed Control of Robotic Networks and Lectures on Network Systems. And he has published over 350 papers. Professor Blue is a fellow of IEEE, IFAC, CM, ASME, and Night Science, and also served as president of IEEE Control System Society from 2017 to 2019. His work has received numerous honors, including the CM, SIAG, CST Best Paper Prize, the IFAC Automatica Best Paper Prize, and also the 2018 Distinguished Scientist Award from Chinese Academy of Sciences. And let's welcome Professor Francis Trubulu, and we can start our talk.
Thank you, Shantine. It's wonderful to have this opportunity, and I wish to thank all of the organizers for selecting me and inviting me today. I would like to talk to you about my work on, let's call it mathematical neuroscience at the intersection of dynamics, controls, machine learning, and uh, and um, and a little bit of neuroscience. That's right. For those of you interested in it, I have placed a link at my website. I placed a link to this slide, so you might be able to better follow. Before I start, I would like to thank all of my collaborators and funding agencies, in particular, Simone, Veronica, Anand, William, and Francesca, are talented young scientists, many of whom are looking for academic positions. I should also say many of the ideas that I am presenting today are available in a slide in a set of lecture notes that can be freely downloaded from my website. The story I will tell you today has 3 chapters. First, I will give you an introduction in motivation and give you some context for why biologically plausible neural circuits are important and useful and interesting. And then I will present to you a relatively mature theory that works for neural circuits designed for optimization problems. It's a top-down theory. It is a normative theory. And I will show you 2 examples of it. And then I will conclude by discussing the more general asymmetric case, which does not lend itself to analysis immediately in general, to analysis as a single player optimization problem, but rather as a multiplayer optimization problem. All right, here we go. So, despite incredible achievements, machine learning is lacking nowadays in interpretability, computational efficiency, and other features that might be desirable. And so this collection of questions that one might ask oneself are, what are optimal ways of processing information given the laws of physics? And how has the brain evolved its strategies to approach these limits? And can we use ideas from how the brain does it, from neuromorphic computing, and from analog computing, from oscillator-based computing, to design new technology for computation and learning? And so oftentimes these broad questions about limits of physics, biologically plausible strategies, neuromorphic computing, oftentimes these questions reduced to cost minimization and energy landscapes matters. Hence the title of my talk having to do with navigating energy landscapes. So here I have 3 references: the work by Sureis, Bettetti, and Gu, illustrating various either images or just this general concept, which is, I believe, very widely established, that the fact that the brain functions to minimize certain cost is widespread and pervades theoretical neuroscience. So this is nothing new, it's widely established. What are these energies? For example, just this very year, well, actually last year, John Hopfield received the Nobel Prize for his work on associative memory, which was based on energy functions, among other things. And so here's one very concrete instantiation of what I am talking about. So imagine we consider, okay, we are now in the context of continuous time, recurrent neural networks of differential equations. And I am interested in particular in this firing rate formulation right here, this firing rate network, which is defined by three elements: a synaptic matrix, an activation function, and there is a stimulus, the stimulus U. Well, there's an input matrix B as well. So now I have this dynamics. This dynamics is widely studied and well known. I mean, the questions are transcription of the questions from the previous slides into this slide, into this context. The translations are, what functionality does this firing rate network implement in general? Can I do some kind of inverse optimality analysis for this dynamics? So more specifically, in general, what energy does this firing rate, whenever I give you a dynamics of this form, what energy is it optimizing? And another question or related question, I am not so interested in a bottom-up problem. So you give me the dynamics and I try to find a layup on a function of sorts. I am much more interested in a top-down approach, a top-down framework. So is there an optimization-based framework to design neural circuits? So in other words, what do I mean by that? You give me a mathematical objective, and from the mathematical objective, under some assumptions of the mathematical objective, then I derive neural circuits that solve that are capable of solving that objective. So that in that sense, I mean top down. In this sense, I mean normative. So you tell me what you want the circuit to do, and then I crank the machine and I deliver for you. What do I deliver for you? The three ingredients: the synaptic matrix, the activation function, and the stimulus. Now, that's the context and the motivation. So I am interested in biologically plausible circuits, and I just mentioned, I just show you in what context. So these are the two special cases. First, I will work on optimization problems, and then I will work on a little bit on multiplayer optimization problems. And I will introduce something called proximal gradient descent. And then we will discuss something called proximal gradient play. Now, I'm going to now take a little bit of a detour, like a prologue. So, like all of a sudden, let me talk a little bit about mathematical optimization, and then we're going to come back to neural circuits. So, suppose you have an optimization problem which is regularized. So, what do I mean by regularized? What I mean is that I have a cost function. Let's call it f. I think of it as a nominal cost function, and it's well behaved, it's differentiable, it's convex, maybe strongly convex. You decide, how well behaved it is, but um, but then I regularize the optimization problem. By that I mean to say I add an additional cost, and this cost is a regularizer, and this regularizer may be poorly behaved. And so, well, there's the whole theory of CCP functions. It's a longer and more detailed story, but for now, for this slide, it's just a regularizer, and therefore I referred to this problem as a regularized optimization problem. Now, here's a very silly example just to get us started. A quadratic function. I have the L1 regularizer. This is in 2 dimensions. These are contour plots. Of course, the L1 regularizer leads to sparsity, encourages sparsity. And as you can see, it's not differentiable everywhere. And then I am interested in the sum, just to visualize. So this is, okay, so now what can we do with this regularized optimization problem? So let me provide, how would I go about solving them? So in order to do that, I would like to introduce something called the proximal operator of the regularizer. And what's funny about it, ironically, it's a regularized problem. So here's what is this proximal operator? That's what it does. You give me a point x, and I try to find a trade-off between minimizing g and remaining close to x. So I look at the point, so the output of this function is a point that is close to the input x, but it is also attempting to minimize the function g. So it turns a point x into a point that is better point from the point of view of the regularizer g. So here I have a picture. Imagine my regularizer is this blue curve, which is the absolute value of x. If I if I plot the function that I am optimizing, then I get a smoother version of it. So this proximal operator has been widely studied. It's been for many decades. And it's a regularized optimization problem. So right now you might tell me, Francesco, I know G, but what is the complexity of this prox? Can I calculate it, or do I need to solve this optimization problem at all times? And here on the right, I have borrowed a table of examples from the book by Beck. And this table of example, it's here just to kind of explain to the audience that, well, okay, there are so many examples in which you give me the regularizer and I can tell you in closed form, in very easy format, what its proximal operator is. So in other words, um, there are cases where this operation cannot be expressed in closed form, but everything I will talk about today, this optimization problem can be solved and has been solved in closed form. I am just referring to the literature on that. There's nothing new. All right, so here we go. I want to minimize with respect to the variable x. I might have an input u, but I want to minimize with respect to x, a regularized problem, nominal plus regularizer. And this is what I'm going to propose to solve that dynamical system. I'm going to propose that we adopt this dynamical system called the proximal gradient descent. It was introduced in a paper by um, um, I'll get to that in a second. Jovanovic at USC. So now, what does this dynamics do? Well, when you look inside the dynamics, you see that the argument, this is essentially a discrete time step of the gradient descent for f. So you take a discrete time step of the gradient descent for f. So you move in a direction that helps f. And then you look for with this better point from the point of view of g. So you apply the proximal operator to a gradient step of f. And this point that you are aiming to, this is the point that you can think of this point as being a target point towards which your continuous time dynamics is evolving. So this proximal target point, right, because x dot equal to minus x plus a, the property of that dynamics is that x will go towards a. Of course, the target point itself is a function of x and u, and so therefore it will be changing, it will be moving, and you track it essentially, you pursue it until convergence. Now comes the interesting observation. If you look at this dynamics, it's an energy system, right? It's an energy dynamical system that is fully determined. It is fully determined by the two energies, F and G. There is no other element in here. Just like if you have gradient descent, it's fully determined by the energy F. If you have natural gradient descent on a Riemannian manifold, well, you need a Riemannian structure. Here I'm not using anything. There are two energies. The two energies give rise to the proximal gradient descent. All right. This is here the work by Jovanovic I was referring to. Now, this is the end of my prologue, of my detour. Look at the two dynamical systems that I have shown to you so far. What are they? One was called the firing rate dynamical system, and the other I am calling the proximal gradient descent. If you look at them for a few seconds, you realize that in reality, they look very similar. And imagine, for example, that f is a quadratic function, so that its gradient is linear in the arguments x and u. So if f is quadratic, And then imagine that this phi, the activation function, is equal to the proximal operator of a regularizer G. Well, then it is immediate to observe that they are the same. So I'm not claiming this is a major theorem. This is really a very immediate observation that any of us can do. So when you look at this similarity now, you start to understand why I went on this detour, because I want to understand what cost is the firing rate function optimizing. And what I've just shown to you, well, it's a proximal gradient descent, which is defined by f plus g, by these two terms, right? Okay, um, what have we figured out? That the firing rate dynamics is in fact the proximal gradient descent for an energy that is a regularized energy. And in fact, I am calling it the Hopfield energy. It's a little bit of a stretch, but it is true that if you go back and you look at the Nobel Award-winning work by John Hopfield, in fact, the energy that he introduced after some changes of coordinates and some manipulation is in fact the same as the sum of two terms. One I will refer to as the network. So just to be clear, this is the f function and this is the g function, the regularizer. And so this is the nominal cost and this is the regularizer, right? And these functions have two features. So let me tell you what the two features are. The network energy, the first function f, captures the interaction among the neurons and the effects of the stimulus. And it's a quadratic function, like I promised in the previous slide. Now, the other function, g, happens to be the sum of it's a separable function. It's the sum of individual functions of individual neuronal activities. And each of those neuronal functions, I'm going to refer to them as E sub activation, give rise to an entry of the activation function, capital phi. So we have an energy, a network energy, and an activation energy. I believe this interpretation is novel. So now, let me give you a quick example. Suppose that I'm interested in, I use as regularizer a cost which is plus infinity for negative. So this is the number 0. This is x. And then a cost that is plus infinity to the right of 1. And it's equal to 0. It's equal to identically 0 between 0 and 1. This is called the 0, 1 indicator function. Then it's well known that the proximal operator for it is just a saturation function. It's just a saturation between 0 and 1. And then, in fact, firing rate models which use the saturation have been widely studied in mathematical neuroscience, and they are usually referred to as the linear threshold model. So there's whole literature just on linear threshold models, which naturally arise from this very simple. Basically, this is saying the activation rate, the firing rate of the neurons cannot be negative and cannot be larger than 1. So there's an upper bound and a lower bound. But other than the upper and the lower bound, you're trying to minimize f, the nominal energy. So here I have a picture. I have a quadratic, oh, pardon me. I have a quadratic function f. You see just a little bit of a patch for it. Outside of the square 0, 1, the function is equal to infinity, right? Because you get the regularizer sends you to infinity. Here, these are the level sets of my quadratic function. And just for fun, you can see that even if you start non-feasible, the black curve is the trajectory that solves the proximal gradient descent. And sure enough, it finds the global optimum of that problem. And in gray, these little gray points that you're seeing, these are the target points that I was telling you earlier. At each point in time, that's the proximal of G of a gradient step for F. All right, just to illustrate it. Okay, so now before I leave this topic, let me clarify. Why am I talking about this gradient descent? Well, now I can know that I have justified my interest for this problem. I can just say that there are a lot of properties of the gradient, of the proximal gradient descent that have been studied in the literature. These first three properties were well known before our work. So this proximal operator of the gradient is well posed. It's a Lipschitz function. So in fact, the differential equation is well defined. It doesn't have any discontinuities. And it's uniquely determined by the two energies, F and G, as we said. The other thing, which is the critical property, this is, again, well known in the study of proximal discrete time algorithms, is that if you're interested in minimizing F plus G, that's the same as finding an equilibrium of the proximal gradient dynamics. And the new property, pardon me, the brand new property that I want to announce today, this appeared in a work by my student Gokle, is that when bounded, so if we start where f is unbounded, of course this statement is not true, but when bounded, the regularized cost f plus g is non-increasing along the flow of the proximal gradient descent. This is important because why are we interested in gradient flows? Well, the key property of gradient flows is that the energy is like rolling down a hill. If I plot the energy landscape and I have a little, like a sphere, this sphere is rolling down the hill and I go to the minimum. So the proximal gradient descent has the same exact property where, as you're plotting the hill, the energy landscape, it's not just the landscape of f, it is the landscape of f plus g, g being the regularizer. Other properties can be established. We, for example, have established a notion of robustability called contractivity under conditions on the synaptic matrix. In fact, the flow along this proximal gradient descent is a contraction. And I will refer you to this work here by Gokle. There is also a version of the PL condition, the Polyak-Lojasevic condition, which applies to this particular case and gives you exponential convergence even when the functions involved, the function f, is not convex. All right, now, yet another very interesting property of the proximal gradient descent, and this is not our work, this is work by Wu and co-authors, recent one, is that in fact it is possible to implement the proximal gradient descent in an analog circuit. Provided you are capable of implementing the gradient and provided you are of the nominal function f, and you're capable of implementing the proximal operator of the regularizer, then in fact you will have 1, 2, 3 amplifiers for each dimension of the problem. So that's very interesting because basically what this is saying is that, okay, from now on I'm going to be talking more about the neuroscientific interpretation of these dynamics, but in reality one could write circuits that would in fact implement this problem. So in summary, what have we learned so far? We've learned that if you give me an energy, a regularized energy of this form, then in fact I can do that normative top-down design that I was talking about earlier, right? I can just from the energy derive the neural circuit. So I'm playing Lego, you give me F and G, and I just, I build my little construction. The network energy describes the interaction, and the regularization captures the physical limitations or encourages sparsity, or, there are a wide range of regularizers studied in the literature. Right? Okay, so perfect. Now, before we continue, and I show you 2 case studies, let me clarify that, of course, when I said that the nominal function has to be quadratic, I meant because it's a quadratic function, the synaptic matrix has to be symmetric because you have X transpose W. W is symmetric. And so this is a big assumption on the synaptic matrix. And in many realistic cases, the synaptic matrices are not symmetric. So, actually maybe in all realistic cases. So we'll come back to that. But I have achieved that normative framework that I am deriving neural circuits from a mathematical objective. That was from a general, not a specific one, not a special case. Right now, we're going to look at 2 special cases, right? And we'll talk about, in some detail, I will talk about sparse signal reconstruction, and then I will briefly hint poly decomposition before we get rid of that symmetry assumption. All right, so here's a little bit of wonderful classic work in computational neuroscience by Olshausen and Field, which shows that signals received by our retinas have the property that they get processed, and in the V1 primal visual area, these signals are being sparsified. And the picture here, you can see, what I would describe as a dense signal, and then at the output of a coding network, the signal is sparse. And this picture is taken from their papers listed below. And in order to do this sparsification, the idea is that the primal visual area V1 has available to it some dictionaries, some receptive fields, which are themselves learned. That's another story. Some dictionaries, and you do sparse coding. So you write your input signal as a linear combination of just a few of those dictionary elements. And that's why just a few of the neurons corresponding to those dictionary elements will fire. The other ones will be silent. So it's an energetic achievement. You encode the signal and only few neurons are firing, so you save energy. And there's more. Okay, I'll come to that in a second. So here's another wonderful picture from the work by Papadopoulou and co-authors, illustrating a very similar concept appearing in insects, whereas the previous computational neuroscience work was for mammals. Now, sparse coding and sparse energy, sparse signal reconstruction has been widely studied in engineering. Here are pictures borrowed from the book by Wright and Ma. Again, the concept is that you have dictionaries, you take an input signal and you encode it only using dictionary. So essentially, okay, so you can identify and exploit sparsity, but I do want to say that this idea of sparsifying the signal is in fact at the heart, that's what Wright and Ma say, at the heart so dimensionality reduction is at the heart of intelligence, the way it's interpreted in their recent book. All right, so now let me just, I have a couple of slides which are a little more technical. And so what is this nominal plus regularizer that I am interested in? All right, here's what it is. You give me a stimulus U is my stimulus. I reconstruct it as a linear combination of columns of capital Phi. Capital Phi is an over-complete dictionary matrix. And I call that my reconstruction cost, which happens to be quadratic, just like I had promised. And then I want just a few of the neurons of the entries of X to be positive. I want, by the way, I don't want any negative output, and I want to enforce or encourage sparsity with my regularizer, which is the one norm of X, like I had shown in the example. This is the classic lasso function, right? Or maybe I should call it a positive lasso because I am constraining the argument to be non-negative. And just so before we leave this slide, there are essentially, just so we understand, there are essentially three numbers in this problem. One number is you give me an input of dimension m. I have many more dictionary elements of m. In that sense, the dictionary matrix is over complete. But out of the vector x, which solves this problem, if sparsity is properly encouraged, very few of those entries will be turned on. And so the vectors are going to be k sparse. So, and then k is much smaller than m, which is much smaller than n, right? So I am using over redundant dictionaries to diminish the dimensionality from m to k. All right. All right, and now I'm going to crank the machine as I had promised, right? This is my positive lasso problem. After I do all of my little calculation, I have to differentiate the quadratic cost, and I have to look up in my table of examples from the book by Beck what is the proper proximal operator. It turns out that you get an extremely simple dynamics. You get a ReLU function, which is widely established. I don't think I need to tell you what it is. You get a synaptic matrix here in a certain form. You get an explicit expression on how the stimulus appears, and you get there's a bias term here which has to do with the amount of lambda is a scaling term for the regularizer. All right, so this is wonderful. I should say this is very similar to a wonderful work done by Rosell and co-authors, maybe about 15 years ago and after. And it's not that this is completely different from what they did, although they were working on Hopfield models, and here I am showing a firing rate. It's just that the point of this discussion is that this model comes out of a general framework in a very natural way, and its properties are already being analyzed because the general proximal gradient descent, I show you all of the properties of that. And this is work by my former PhD student, Veronica Centorino. Right, and then if you write that in components, you get a very wonderful, very specific mathematical neuroscientific interpretation. So as I said, lambda is a bias. Phi I is the dictionary element that describes neuron I. And so the more similar is the stimulus U to the dictionary element of the neuron I, the larger is the effective stimulus that neuron I receives. And instead, if phi j is very different from U, then neuron J will receive no stimulus. And then finally, what is the interaction doing here? Well, under non-negativity assumptions on the dictionary elements, it turns out that this is always negative. And what this means, the more similar dictionary element I is to dictionary element J, then the stronger is the lateral inhibition that I and J are exerting on each other. And so this is a little bit of a, okay, I've tried to illustrate that with my picture here at the bottom. But basically, right, neurons are receive an input, a stimulus. If their dictionary elements is similar to the input, then they get excited, and then, but they get repressed or inhibited by other neurons. It's a competition that is modulated by this ReLU function. And in the end, in fact, this is guaranteed to, well, under standard isometry conditions from signal processing, this is guaranteed to converge to a nice sparse signal. All right, let me show you a second case study here. So this is inspired by the work by Friston and by the recent work by Chaffier and co-authors. And this has to do with the free energy principle. And so the objective is to show that so the free energy principle is a general theory in theoretical neuroscience and computational neuroscience. And there is, people have published papers with empirical evidence for the free energy principle. And the question is, can I write an F plus G? Can I cast this into my framework of deriving neural circuits from optimization problems? So first, this slide is a very general slide. It says that basically we're in the context of probabilistic mind theory. We are imagining that the mind treats information as probabilities and does some kind of Bayesian inference. There is an energy. This energy determines an optimal policy for the agent. Let's just keep it at the level of agent. And this energy captures some notions of expected loss, a model of the environment that is kept in the mind of the agent, which I'm going to refer to as generative model, a model of, a nominal behavior and a model of the environment. Forgive me. Now, the free energy principle says that adaptive behaviors arise in agents, arise from minimizing the free energy. There's an interpretation of the free energy as surprise, but I think I don't have the time to go into the details right now. I'm only going to say that the free energy principle is applicable broadly, for example, to perception problems, learning problems, decision problems. I'm going to be talking about precisions, and specifically, I am interested in a specific problem called optimal policy composition. And this is the work of my student Francesca Rossi. And here, okay, so here, let me know, I don't have time to define all the symbols. Let me just say that I have a nominal cost, just like, we've had so far, which captures a surprise, an actual outcome that is surprising with respect to a prior belief. And then there is a regularizer, and the regularizer is related to entropy. So here the regularizer says maximize uncertainty. So I am unsure about whether I want to take, I don't want to take I don't want to have a deterministic pure policy. I want to have some uncertainty. So I maximize entropy. Tau is the temperature of the entropy, which is the coefficient of the regularizer. And my decision making, I am deciding a policy to make decisions. And this policy is a convex combination of primitives. So basically here, my actual policy will be a mixture of policy, a mixture of experts. I am listening to multiple experts and coming up with an appropriate convex combination. So W, the probability, these are weights. I am choosing convex combination of the primitives. All right. The optimal policy composition. This problem is an optimization problem on the simplex, right? Because W is a vector of probabilities. So on the right, you see a wonderful little picture that illustrates how, in fact, all trajectories will converge to the global minimum of this cost function, which is defined on the simplex. Here, I just have for the picture on the right, I just have three policies that I am mixing. And the resulting, well, now I can again crank the machine, right, and derive my firing rate neural network. There's a little more detail. I refer you to the technical report and upcoming submission. This particular dynamics, right, is on these policies, w dot equal to minus. I have my here. This is the step of the gradient descent for the surprise, and then the regularizer for the entropy. And there are some details that I'm swiping under the rug, is the softmax activation function, which is widely studied in machine learning. And we discuss more details on this in that paper. So this is a wonderful second case. I just don't have the time to go through the details, but this illustrates that the general framework can be applied to multiple examples. All right, I have 10 final minutes in my presentation. Let me start by going back to the general formulation and saying that, okay, I wanted a normative framework, and I derived one which seems to have some expressive capabilities. But there is something that happens in realistic neural circuits which I am unable to capture so far. And this principle is called Dale's law. And this law says that a neuron has the same type of effect, either inhibitory or excitatory, on all of its neighbors, right? So this is called Dale's law. It's an empirical law. I was talking to some colleagues. It's not a mathematical law with 100% guarantee that it is satisfied. I think if one goes through the literature, there are a few counterexamples, but they're sparse and a few between. So it's not very. It is a law that is very widely accepted and verified empirically. Hmm? So now the question is, so in other words, for example, even all the way to the classic work by Wilson and Cohen in 1972, you might have that your network is described by two neurons, or I should say two neuronal populations. So as I begin speaking now, whenever I say neuron, I mean to say, well, individual neuron, that's certainly fine, but I actually mean neuronal populations. And there's some kind of spatial temporal averaging that leads to just a mathematical description with just two states. And that's in fact the work by Wilson and Cohen in 1972. So I could be studying an excitatory-inhibitory pair. So this is called an EI pair, EI network. Or I could study very interesting motif here. I have an inhibitory neuron in the middle. I have two excitatory neurons on the side, right? So the central inhibitory neuron mediates, and it's basically, let's say, the neuron on the left excites the inhibitory neuron, and the inhibitory neuron inhibits the neuron on the right. So, by the way, when I draw this, the semantic for this meaning, for this symbol is inhibition, right? And so here you're this circuit is widely and loosely understood to achieve a winner-take-all behavior. In other words, either the neuron on the left is on or the neuron on the right is on. Because if any one of the two is on, then the inhibitory neuron will also be on, and then that it will inhibit the other, right? So this is widely studied as lateral inhibition, but perhaps there's some simple mathematics that we can do to immediately convey what is happening here and establish that without doubt, and we can also understand for what synaptic weight does in fact this behavior take place. Now, I should say before I continue, now that I have asymmetric networks, I have EI networks, well, a very rich dynamical behavior is possible, not just monostability, where I have a single unique globally asymptotically stable point, all trajectories go to it. I might have multi-stability, limit cycle, chaotic behavior. And in our work by my students, Bettetti and others, we study that. But here, I'm just going to focus on one, as you will see. Rich behavior is possible, but in general, I will say that there is a lack of a general analysis framework for stability and functionality. In other words, it's really not clear whether this network is stable in general, which one of those behaviors will take place, and what is its functionality. It's really not clear in general. And certainly, and I won't be able to propose it today, there is no general top-down normative framework. So think of that as a very broad general direction of research that is, all right, I'm going to show you in the next 3 minutes, I'm going to show you 3 results. The first result is an interpretation of what's happening. The second is stability. The third is functionality. All right, the first result is that this is the picture that I've been painting for the last 35 minutes. There is a proximal gradient descent. When the network is asymmetric, you can imagine that each neuron has their own individual cost function, sum of a network cost and a regularizer and activation cost. And each neuron is doing a proximal gradient descent for its own cost function. And so now this is called a game, right? This is called a game in which different neurons are optimizing their own individual costs. The formulas are very similar. They're not identical, of course. We are referring to this one as a gradient. So the word gradient play is standard in game theory, but this is a proximal gradient play, right? Because I'm doing proximal gradient descent for each of the players. And here's an illustration, and I'm not going to have time to go to really explain what is happening in here, but on the left, it's a classical picture of, the ball rolling down and minimizing a cost. And on the right, and you have a single cost with a single set of level surfaces. On the right, here you need to imagine that there are two variables. There is a neuron that moves along this direction, the orange one, the excitatory, and then there is an inhibitory neuron that moves along the other direction. There are two contour plots at the top and two level surfaces, and basically neurons are trying to optimize their respective cost, and in this particular case, they achieve a Nash equilibrium. So for those of you, right, and here at the bottom is the link to the report. All right, so we have a new interpretation, but it's also interesting to say that we have new results on monostability. So what do I mean by monostability? Monostability, I mean the existence and uniqueness of a globally asymptotically stable point. What that means is that no matter where you start, you will always go to the same unique equilibrium point. And the conditions that we get are predicated upon two assumptions. So we are able to study EI networks where connections are reciprocal and synaptic weights are homogeneous. So I'm going to leave it at that because my time is running out, and would be more than delighted to take any questions. The reciprocal connection, if ij is an edge, ji is also an edge. And then every time I have an excitatory to excitatory connection, the weights are always the same. So I'm not able yet to handle the heterogeneous case. And so then what we have here, we have a very simple set of conditions on the WEE and WII weights. They need to be not too large. If those weights are not too large, then the system indeed is monostable. And when I say the system, I mean to say the firing rate dynamics that I've been working with for the last 40 minutes that now satisfy Dale's law, right? Satisfying Dale's law. And how low do they have to be? Well, that depends upon the degree. Let me not go into too much. It's a beautiful network scientific result here having to do with the in and out degree of the nodes of this network, general network. So long as these numbers are small, I have monostability, globally asymptotically stable. All right. So hopefully I have another minute. Let me tell you what can we say about functionality. So for the EIE topology, super simple. And here I've added all of the weights, but I have, more importantly, I have added the stimulus, right? There is a stimulus that hits the left and a stimulus that hits the right neuron. So then what do I have in here? I've simplified the conditions from the previous slide. Just that I have WEE less than 1 gives me monostability, and I need another condition in order to achieve the functionality that I'm about to describe. So for those parameter values, what I achieve is I achieve that in fact I have discrimination, contrast enhancement between the left and the right input. When the left input is a little larger than the right input, then in fact the globally asymptotically stable equilibrium point has the feature that the left neuron is high and the right neuron is low. So I have, and what is that discrimination parameter? Delta. Well, I have an expression for that gap that describes when one of the two inputs is larger than the other by a certain amount, then in fact this difference gets highly amplified and that neuron is the winner. This works not only when I have two neurons, but the same analysis goes through when I have k neurons that are competing, a winner-take-all problem. So you have the same condition, monostability and functionality. When I have more than two neurons, well, the only difference is that I need two delta. So when neuron I is larger than, when the stimulus to neuron I is larger than the stimulus to neuron J by twice the gap delta, then in fact the globally asymptotically stable point is the one for which the excitation of neuron high is high and every other neuron is low. And finally, if I may, and then I will quickly conclude, if I have an input, a stimulus that is not very widely differentiated, perhaps you have two signals that are very similar to each other, it turns out that you can show that even just one of these layers of this column of EIE motifs increases the difference between the two signals. And so here at each layer, you are increasing the distance between the left stimulus and the right stimulus as they get propagated through the column. And under very similar well behavior conditions, what I can show is that, okay, again, imagine that I have that left and right here, left and right are different by a very small amount. Then, in fact, after a certain number of layers, and I have an expression for it, then in fact the signals that are being propagated along these edges are now sufficiently differentiated, and therefore after one additional layer I achieve full contrast enhancement. The left neuron is equal to 1 and the right neuron is equal to 0. All right, I see that my time is up and I have told you a story, a little story. I've given you some context and some motivation for biologically plausible circuits. I have shown to you this general top-down framework, proximal gradient descent with normative and regularizer. I've shown to you two case studies. And then I have generalized that to the case of multiplayer optimization, where I have given you a nice interpretation, stability and functionality for contrast enhancement, but I did not really deliver on a top-down framework yet. That I am still very interested in. We are very interested in general systems theoretic problems in neuroscience. We're interested in connections with machine learning and connections with non-conventional and analog computing that we hope this theory will enable. It's 9:48. I am 3 minutes late. I apologize. I'm available. I know Shanting will now relay some possible questions, but you can easily send me email. I'll be happy to follow up. And you can find these slides right now on my website. Thank you so much for your kind attention.
Thank you, Professor. It's a really interesting talk, and I'm gonna pass some questions from the YouTube live to you. The first question is from Andrews. Thank you for the great talk, Francisco. I was wondering, how does the free energy principle relate mathematically to classical stochastic optimal control or dynamic programming? Is there an explicit mapping between belief updates and proximal steps?
That's a wonderful question, and I offer you my sincere apology. I am not a great expert on the free energy principle. I believe there are connections. and it's quite an exciting topic for control and systems theoreticians with an expertise in stochastic calculus and stochastic and dynamic programming to look into. It's a theory proposed by a widely established a neuroscientist, Carl Friston. My collaborator Giovanni Russo at the University of Salerno has a lot of knowledge in this field, so I will refer that question to Francesca and Giovanni.
Okay. Another question is the model earlier on, in the model earlier on, we were able to say a lateral inhibitory effect, but not lateral excitatory effect. Would it be reasonable to have lateral excitatory effect?
Excitatory effects.
Yeah.
In my humble and limited knowledge of neuroscience, you usually have lateral inhibitory effects. And the point is that you have a stimulus. Sorry, I didn't have time to explain that. You have a stimulus, and you need to decide whether this pathway turns on and that pathway is inhibited, or the other way around. And so this you can find wonderful information on the web on lateral inhibition and competition between different hypotheses, between different pathways. And so yes, to the best of my limited knowledge, I don't believe lateral excitatory connections are as widely studied. Nevertheless, let me say that I've shown you three examples here, EIE, EKE, and columns of such, but the general theory of monostability that I have shown to you here is applicable to any arbitrary topology of EI networks.
I have one question. So in your form, you have the network cost and also you have the act act activation, that one. So I
Mhm.
was wondering, like, in this activation, when you find the pathway to reach to the optimal point, you can also find the way, like, how the neuron they reach the task. Because I know some people they like language model really is really popular now, but people they are wondering if you lack of interpretability a
Yeah.
lack of safe guarantee. So they want to know like how do you really reach to the task? Some people they design some really simple tasks, sequential one, and they disable some neuron, they
Yeah.
enable some neurons. So they
Yeah.
kind of I wonder like your study in this mathematical analytical form is something related to that?
Yeah, Shanting, this is a really marvelous question, and you pointed the finger precisely at well, this is what you have just described is what we would like to do, and unfortunately today I fall short of that. I am not able to get all the way there to what you have described. But if I allow myself to go back to one of the early slides, then in fact, you know, it's precisely this point, right? That deep learning models, such as large language models, are not very interpretable. And what I've done today, I believe what I've shown to you today is very interpretable, but of course I have not been able to, I'm not today able to claim that large language models are, a proximal gradient descent or something related to that. So I'm looking at a much more contained scope, but we would very much like to provide a deeper understanding of more general architectures. Today, I have focused my attention on firing rate recurrent neural networks. Um, there's lots of interest in gated networks. There's lots of interest in all sorts of more general architectures. Forgive me, Shanting, I am unable to I would like to, but I'm unable to answer your question.
Thank you. There's another question.
Mhm.
How sensitive is the proximal gradient descent equivalence to noise or perturbations in your activity? Does the biological system has built-in
Right.
robustness that the mathematical model can capture?
Now, this is a wonderful question, and I am so thankful to receive it because it allows me to boast about some other work that I've been working on. So, um, clearly, the robustness of the dynamics will depend upon the ingredients F and G that's necessary. However, I will say that with some caveats, and I can clarify, in both cases, that I have illustrated today, the sparse coding and the free energy policy composition, we have versions of the contractivity property. And the contractivity property is a very strong, robust stability property, which ensures, for example, very nice response to noise, very nice response to perturbations, whether they're stochastic or deterministic, very nice responses even to unmodeled dynamics. So suppose that I have this idealized proximal gradient descent, but the real circuit, of course, has all sorts of other elements that generate additional dynamics. So in control theory, we would refer to them as unmodeled dynamics. And contracting systems are very robust with respect to perturbations, unmodeled dynamics, delays. There could be delays in the transmissions of signals from one neuron to another neuron across the network. There are robustness results of contracting dynamics with respect to all sorts of perturbations. And I will clarify the caveats that I mentioned. Two things. One is that in the case of the free energy example, the policy composition, I called it soft max gradient descent. That is a strongly contracting dynamical system, and it has a very strong robustness properties. And instead, for what pertains the sparse coding example, right? That dynamical system happens to be strongly contracting. There's a conjecture in here. It's strongly contracting when you are moving among vectors of activations X that are sparse. So long as you're moving, just long as you're in the space where just a few vectors are activated, just a few neurons are activated and the others are silent, then you are strongly contracting, you can handle everything. And in numerical simulations, this is easily seen to be always the case. And there are a number of works on related topics, in general, proving that you only remain on that, let me call it manifold, even though it's not a differentiable manifold. That is hard to do. So there still are mathematical problems, but in practice, the behavior is extremely robust.
Thank you, Professor. Since the time is approaching, let's conclude with one last question. Dear Professor, what are the distinct differences and challenges when scaling from one single agent optimization to a multi-agent optimization problem?
What are the challenges? So I believe we have developed a wonderful, let me just go back first of all, we are focused on these EI networks because of Dale's law. We would like to understand, so as I said, a general framework is essentially, okay, of course there are elements, of course, right? But there certainly is no top-down framework that tells you, I tell you what I want to achieve, and then I crank the machine and I get a circuit. That is totally, to the best of my limited knowledge, it's not available. I think there are, of course, stability results, and here we have leveraged the decades of work in control theory, stability, Lyapunov diagonal stability, and so forth. I think this idea of functionality is important. So I think that our interpretation of multiplayer games will help with understanding the functionality. But yeah, we have, so going back to the question, I think I've shown to you some results, some stability results, some functionality results. There are more. We have some limit cycle results in the paper. I would like to move towards a general top-down framework, and I would like to move towards more general dynamics, not just firing rate. So as I said, gated networks and other more general architectures that maybe I can actually go to the final slide now that I remember. There are all sorts of other computational paradigms. Astrocytes, dendritic computations, Hebbian learning, equilibrium propagation. There is a broad range of biologically plausible strategies that we are studying and would like to understand.
Thank you, Professor. I think I really enjoyed today's talk because it's really new for me. Like people from control this different angle to deep into the neural structures, how to do the interpretability. So I really enjoyed the work and looking forward your future work and explain like now you have like convex that's like some properties, but maybe you can extend the future work. And I'm looking for that. Thank you so much, Professor.
Thank you so much, Shanting, and all of the organizers for inviting me today. Bye bye.
Bye bye.